In this video lesson, we're going to be taking a look at some further details of ionization energy. So we'll look at the first ionization energy, but we'll also look at successive ionization energies. All of this material, the images that we see throughout the video are from our textbook, Cognitive Higher Level Chemistry. So first we'll look at emission spectra. So remember that each element has its own distinct emission spectrum, and that's based on the energy transitions of its electrons. So we remember when an electron is excited, it absorbs a photon of energy, jumps up to a higher energy level. So that's the absorption spectrum. It'll absorb those photons of light, and you would see dark banding in the continuous spectrum. But in an emission spectrum, when the electron drops back down to the lower energy level, it releases the photon. So then you see the bandings of light. So that means that the transitions are quantized. They have specific energies, and only certain energies are allowed. So the energies are related to the different energy levels in the atomic atom. So the image on the right is not how the energy values are. They're not. It's not like a slide where the energy just slides continuously down. Instead, there's jumps in energy as the electrons jump from one energy to another. So the example we'll take a look at is hydrogen. So remember, there are different sets of lines formed in the infrared, which is over here to the left, the visible spectrum, and the ultraviolet spectrum. As the energy increases, and they're going this way, note how the lines begin to converge until eventually they're all converged together. So that is one question that often comes up on the IB assessments is, as the energy increases, what happens to the lines in an emission spectrum? And that is, the answer is they converge. So when electrons get excited and jump to higher energy levels, they will jump down to different energy levels, but the only ones that we can see that are visible to us are the ones that jump down into energy level n equals 2, because this is in the range of the visible spectrum. So that is called the Balmer series. So that represents when an excited electron reaches the n equals 2 energy level. So most of these lines are in the visible spectrum, and this is what we see when we look at an emission spectrum. The Lyman series represents when an excited electron reaches the n equals 1 energy level. We can't see these ones though because this is in the UV range, so they're invisible to us. So the convergence limit of lines is up here, so as you approach n equals infinity, those lines are very, very close together. So the convergence limit is the point at the high end of the Lyman series where the lines converge together, and it's identified as n equals infinity, like I said already, on an energy level diagram. And this value, along with Planck's constant, can be used to calculate the first ionization energy of an atom. So when we calculate ionization energy, that represents the point where the electron has surpassed the n equals infinity limit and has left the atom. So remember, we've pulled the electron right off the atom and it's left. So that is equal to, so energy in joules multiplied by Planck's constant in joules times seconds multiplied by the frequency in per second, seconds minus 1. So note that the Planck's constant and this equation are found in sections 1 and 2 of the chemistry data booklet. So if you were doing a calculation, you would be prompted in the question to go find that information. So here's an example, the example given in the cognitive textbook. So it says the frequency of the convergence limit in the ultraviolet series of lines of the hydrogen spectrum is 3.28 times 10 to the power of 15 seconds minus 1. Calculate the first ionization energy of hydrogen in kilojoules per mole. So when you perform the calculation, you get your answer in joules. You'll have to convert that to kilojoules. The value that's calculated using that equation is for 1 atom, not for 1 mole. So you'll need to multiply your answer by the number of particles in a mole. And then if you're given the wavelength for the convergence limit, you'll have to convert it to frequency using this equation, which is also found in the data booklet in section 1. So first of all, solve for the energy in joules. So that's equal to the Planck's constant times the frequency. So Planck's constant, if you look in section 2 of the data booklet, is 6.63 times 10 to the negative 34 joules seconds. And the frequency is 3.28 times 10 to the power of 15 cycles per second, so seconds minus 1. So that is equivalent to 2.17 times 10 to the power of negative 18 joules. Now that sounds like a really small amount, but remember that's per atom, so we need to multiply by the Avogadro constant to find the energy for 1 mole of hydrogen atoms. So the ionization energy is going to be equal to 2.17 times 10 to the power of negative 18 joules times 6.02 times 10 to the power of 23 particles per mole. So that's going to be, for each mole of hydrogen atoms, 1.31 times 10 to the power of 6 joules per mole. But remember, we need to convert that to kilojoules per mole. So we'll divide by 1,000. So it's equal to 1.31 times 10 to the power of 3 kilojoules per mole. So there's a few steps involved. None of the math is overly hard. We just need to remember each of those things to bear in mind. So you calculate the energy, but then you're not done because you have to apply that to the number of particles in a mole, because that's only talking about 1 atom, and then you need to divide by 1,000 to get your answer in kilojoules per mole. So now we'll look at successive ionization energies. The first ionization energy is the amount of energy that's needed to remove 1 mole of electrons from 1 mole of atoms in a gaseous state to make 1 mole of 1+ ions. And these reactions are always endothermic. So for example, if we have calcium becoming oxidized to be a calcium 1+ ion plus an electron, the ionization energy, or the first ionization energy, is 590 kilojoules per mole. And then you can successively remove electrons until only the nucleus remains. And the ionization energy will become increasingly larger as you remove more electrons, because it is harder and harder to remove electrons closer to the nucleus. So we can also plot successive ionization energies on a graph. And you can see here with sodium as our example, there'll be a bigger jump of ionization energy as you move to the next energy level. So when sodium lost its first electron to the second electron's in the next energy level, there was a big jump. And then it still increases, but the jumps aren't as large until you get to the next energy level. And then the last two, the ones that are closest to the nucleus, would be these last two. So this would be the 3s, this is the 2s and the 2p, and then the 1s. So now we'll take some time to explain the trend. So when the valence shell is full, it's very difficult to remove an electron, but when the valence shell only has 1 electron, it's very easy to remove it. So this is sodium again, there's only 1 electron in the outermost shell, so it's very easily removed. And then in the next energy level, there's 8 electrons. They're less easily removed, but then the ones that are closest to the nucleus, they're very difficult to remove. So easy, harder, so there's a jump, and then really hard, so there's another jump. We can also use the graph to make predictions. So we can look at a graph to predict the sub-level that an electron is being removed on. So in this example from Cognity, you're being asked to predict which sub-level electron number 1 and electron number 11 are being removed from in the example of magnesium. So first off, it would be easiest if you drew the electron configuration for magnesium so you can figure out where those electrons are coming from. So magnesium has an atomic number of 12, so the electron configuration would be 1s2, 2s2, 2p6, and then 3s2. So the first electron that is removed would be from the 3s sublevel. Then all the way up here to electron number 11, it's in the last energy shell. So there's just 2 there. So that would be from the 1s. So that's how you solve those ones. So for some additional practice, you can go to Cognity and complete the section questions for section 12.11 and 12.12.